The star of our introduction to the molecular structure and bonding chapter is Professor Stefan France. Dr. France was born in the Bronx in New York City, obtained his BS from Duke University in 2000 and his PhD from Johns Hopkins in 2005, and is currently a professor at the Georgia Institute of Technology in Atlanta, Georgia. And his paper that we're going to focus on today is titled Synthetic Methodology Enabled Discovery of a Tunable Indole Template for COX-1 Inhibition and Anti-Cancer Activity. This paper was published in Bioorganic Medicinal Chemistry in 2022, volume 57, and the page number you see there, and I'll post a link to the paper in the video description. So let's unpack this a little bit and talk about what's going on. First of all, COX-1 inhibition and anti-cancer activity. Anti-cancer is pretty obvious. COX-1 inhibition is associated with pain relief, fever reduction, drugs in this class, drugs like ibuprofen. For example, the COX-1 pathway is intimately tied up in all of those responses to disease, for example. And what the France group wanted to do here, together with collaborators, is develop a tunable structure, a structure that they could easily modify to develop a suite of drugs with potential COX-1 inhibition and anti-cancer activity. And the name of the game here is something called structure-activity relationships. A structure-activity relationship is a rational trend in the activity of a compound as a function of its structure. So if we can create a number of different structures that have, for example, small differences between the various structures and detect a pattern in activity, we've established what's called a structure-activity relationship. In this particular paper, France and his collaborators were looking at Indole, which is a heteroaromatic system consisting of two rings, one of which contains a nitrogen atom. And they had developed some new synthetic methodology and used new synthetic methodology to create some of the substituents that you see on this ring, the groups coming off of it, and vary those substituents in a systematic way. This is what we mean by tunable. We can take, for example, the R group connected to oxygen and make it a variety of different things in a very simple way. We don't need to redesign completely the way we make the compound. We just need to change, for example, one reagent. Same with the X atom in this structure. They were also able to create indoles with other substitution patterns, substituents in other positions, for example, and with other structures. So this allowed them to build up a pretty substantial library of indoles that could be tested for COX-1 inhibition activity and anti-cancer activity. So after they synthesized all of these compounds, they carried out a bioactivity assay to see how active these compounds were in these biochemical applications. So as we dig into this chapter, this unit, some things that we'll be able to notice that tie back to this paper. All of the structural concepts that we'll develop will be used throughout the course and throughout Organic 1 and Organic 2 to understand structure and connect it to properties, reactivity, and, for example, bioactivity. Although those connections can be rather complicated to make. But for now, basic concepts that you may recall from chemical principles 1, like geometry, hybridization, polarity, dipole moments, these kinds of things. These are directly relevant to our understanding of structures like the indoles you see in this paper. And so really firming up those foundational concepts from chemical principles is going to be a major goal of this first chapter of the course.